I'm hoping that Lewis structures are starting to catch on for you. Usually, if you can draw those valence electron dots correctly around the central atom, everything kind of falls into place and the bonds form where there are single electrons, they match up and share, and it's great. I wanted to look at 2 examples of molecules that don't work out when you try to do this dot structure. One example is carbon monoxide, CO. It exists, nobody's going to dispute that. Carbon monoxide is CO. And so for all the rule followers out there, they try to start drawing the dots. Carbon has 4 valence electrons, 2, 3, 4. Oxygen has 6, and we know that they're organized as 2 singles and 2 pairs. And you say, this is great, I can bond these single electrons, we can connect the dots, we can connect these dots, and then, if you start looking at your molecule, your oxygen is full, but carbon is not. That carbon atom still needs 2 more electrons for an octet, and carbon must have an octet. So now we're a little stuck, aren't we? If I were to give that carbon an octet, I would need 2 more electrons. I'd need 1 more here and 1 more down there. But I don't have those 2. So here's another option. If you get stuck, or you draw something and you're just not sure if it's quite right, add the number of valence electrons in the structure. So for example, carbon has 4 valence electrons. Oxygen has 6 valence electrons, for a total of 10. Okay, so now this whole electron dot thing is sometimes called the localized electron model. And often it works. You know, you link up the single dots and it's great. But true covalent bonding does not necessarily mean that the oxygen must contain 6 valence electrons localized around that particular atom. It does not mean that the carbon needs to have 4 valence electrons, 4 dots, localized around that carbon atom. True covalent bonding is all about sharing. So they pool together their valence electrons. And yes, carbon does bring 4 valence electrons and oxygen brings 6, for a total of 10 electrons. But we can organize those 10 however we want. We don't have to break them apart 4 and 6, because that doesn't work. That's not going to give both atoms an octet. So here's where this localized dot model kind of fails us. And true covalent bonding is about sharing all 10 valence electrons however we want, so that we can distribute those 10 and give both atoms an octet. Right now, the way that I have this drawn, my atoms have an octet, but I used 2, 4, 6, 8, 10, I used 12 electrons. That's not right. So this double bond is not the correct structure. If it were a double bond and I needed to give both atoms an octet, I would have needed 12 electrons, and I don't have that. With just 10 electrons, the double bond didn't work because carbon did not have an octet. So here's my suggestion. If you get stuck, try this electron count option. Count the number of valence electrons for all the elements in your molecule, and then just try something. Try guess and check. So this double bond, that didn't work. I don't know, try a single. Give it a single bond. The atoms need an octet. So you go around, you give them an octet. Gorgeous. There are 2 rules of an acceptable Lewis structure. Rule number 1, the atoms need an octet. Unless they're small atoms like hydrogen or like beryllium or boron, they might be okay with less than an octet. But carbon and oxygen will always take 8. So, okay, check. I have octets. But then rule number 2 is that there's only a certain number of valence electrons that you have to play with. We only have 10 valence electrons. So now we count the amount of electrons we used in our structure. 2, 4, 6, 8, 10, 12, whoa! 14. That's the wrong direction. That's not right. So if a single didn't work, a double didn't work, try a triple. Carbon, triple bond, oxygen. And then I have to give them octets, so each carbon and oxygen will need a lone pair, and it doesn't matter where you put them. You can put them on the sides, on the top, on the bottom, that doesn't matter. I have octets. 2, 4, 6, 8. Here it is. 10. Here's the correct structure. Now, these will come up later on in the study guide, but I kind of wanted to mention them in a little more detail now. They're these goofy molecules that they work. It is a triple bond. It's just fine. But they're not easy to predict if you were really sticking to that dot model, where the carbon needs 4 dots and the oxygen needs 6 dots. Yes, we have 10 valence electrons, but we can organize them however we want. We can distribute them however we need to give both atoms an octet. Here's another one that'll kind of follow this same suit. O3 is the ozone molecule. And so again, you might start thinking like, okay, oxygen, oxygen, oxygen. I usually start with the dot model. Okay, so oxygen usually has 6 valence electrons. Maybe I'll actually put my singles on the outside, and I'll put my pairs on the top and bottom. Let's try this. And so then here I got 2 singles and 2 pairs. So I could connect these guys. And then I somehow have 2 singles, 2 pairs. Connect those. You see the problem, right? The oxygen in the center is done. But on the outside, those 2 oxygens still will have 7 valence electrons. They need 1 more for 8. We've used up all our dots. And sometimes people will try this funky thing where they like connect those single dots, and that's really not how the molecule exists. So again, if you're stuck, try counting electrons. Let's do an electron check. Oxygen has 6 valence electrons. There are 3 oxygens, so we'll just say times 3. For a total of 18 electrons. We get to work with 18 electrons. We can distribute them however we want, as long as each oxygen gets an octet. This double bond, or these 2 single bonds, hello, these are not going to work. Because right now I used 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, yep, 17, 18. But I do not have octets. If I were going to fill in these oxygens, they would each need 2 more, and that would give me 20 electrons. That's not right. The single bonds won't work. So again, you just try stuff. Get creative. I don't know, let's try, try 2 double bonds. Oxygen in the middle is done. He's got 8. And on the outside, these guys will need 2 lone pairs. Rule number 1 of a proper Lewis structure, everybody has an octet. 6, 8, 10, 12, 14, I have octets, but then rule number 2, I got to use 18 electrons. This one's short. That one's only 16. It's not right. Now, some people will say, okay, well, you have 18, so I don't know, let's just like throw an extra pair of electrons on here. I don't know. Maybe they'll do that. So they would have drawn something that looks like this, where they were like, oh, wait a second, I have another electron pair. I'll throw it on that central oxygen. But do you see why this one is also not acceptable? This, sad face. Oxygen can only take an octet. You overloaded the central oxygen. So this one was originally wrong. I had an octet, but I didn't use the right amount of electrons. This one did use 18 electrons, 18, but I did not give that central atom an octet. I gave him too many. Wrong. You can try triples, you can get kind of creative, but you might find that this one ends up working. They don't have to be the same. I mean, like, you could try a single and a triple, but again, you can't do two triples because oxygen can only take an octet. So let's check electrons. This oxygen is going to need 6 more. Now this time in the center, I do need a lone pair, but now my oxygen does have an octet. 2, 4, 6, 8. And then this guy needs 2 more pairs. Everyone has an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. Here it is. Smiley. It's actually a single and a double. And we'll talk about this molecule a little bit more, both of these, a little bit more later on in the study guide. But I wanted to show you this guess and check method. If you're ever stuck on your Lewis structure, count the total amount of valence electrons for all the atoms in your molecule, and then just start drawing something. Draw single bonds, draw doubles, draw triples, and then count the amount of valence electrons. A proper Lewis structure will use the right amount of valence electrons and give all atoms an octet that need an octet.